Hi, am I audible?
Farhan, are we audible to you?
Yes, I can hear you. Can you hear me?
Now we can hear you. Now, at least I can hear you now.
Okay, cool. Thank you so much. So we're just going to wait for a little while. Let everyone join, and then we will continue from where we were on Monday. Okay, so I hope everyone can hear me. Do let me know if there is any issue with the audio. But there's a link in the chat. This is the notebook that we are going to use for today's session. So I would like everyone to again go to Google Colab and open this new link. The process remains the same. Just make sure that you are opening the right one, which is on the master branch and within the folder W2S1. And I'm sharing the link on Slack as well. So again, you have to go to File and then Open Notebook, then GitHub. And when you paste the URL, you will see a bunch of notebooks being listed. You can, in fact, so I already have it open, but when you list the notebook there, when you add the URL, then you should be able to see a list of notebooks. So make sure you are picking the right one, which would be within. Yeah, so on Monday we were facing some audio issues. So I hope that doesn't happen today, but do let me know. All right, so I'm again pasting the link in the chat box. Please open this notebook. We sort of completed the implementation for the foosball class on Monday, And what we are going to do today is try to attempt to interact with the environment, try how if the environment is behaving according to the rules that we had programmed, and then we are going to attempt to solve the problem, which is basically see if we can algorithmically control the agent and if we can take it from the starting position to the goal position. So please open this notebook. You will see something like this, what I have opened over here. The difference is that the notebook that we were using last week, it had a lot of to-dos because we were completing the foosball class. In this notebook, the entire foosball class is already present. I'm going to talk about a couple of changes that we didn't discuss on Monday, but otherwise it's pretty much the same. Okay, so I'm going to go ahead. If anyone is facing any issues, let me know in the chat or unmute yourself and let me know. But yep, sharing the link again. Link is in the chat box in Zoom as well as on Slack. Right. So I'll just try to you know start executing, and we have gone over the description and the rules and everything. So I'm not going to go over that again. But then I need to execute this first cell where we had the definitions. Okay. Yep. So my notebook is connected. The first cell is executed, and then I just want to do a very quick 1 minute tour of what the full foosball class looks like. So this is the class. There were two helper methods that were already there for converting between rows and columns, and a single integer that we were calling the state of the game. Then we implemented a method called deserialize. What deserialize was meant to do was it would take a description like this one. So there would be a string for agent, another one for opponent, another string for goal, and there would be a list representing the field. And it would convert this thing internally into a variable called map. So the map will have the position of all the players and the goalpost. The map will not store the position of the player because the position of the player keeps changing every step. So we want to store that separately. So that is what deserialize did. So this is basically capturing the rows and columns and then computing the number of states, which is just the product of rows and columns, and then just storing the map which is being passed. So storing it as such. And then there was a for loop over here, this for loop. So this for loop just scanned the entire field and identified where the player is, where the opponents are, where the goalpost is, and stored them in the corresponding variable. Right. So the player was stored in the initial state variable. The opponents were stored in a list called opponent states, and the goal state was stored. The goal state stored the position of the goal post. And we did this because we want to come back and perhaps later change this definition, create a larger field, or play the position, or place the players differently, and we still want our code to work. So we don't want to hard code anything. Right, this is what dclize was doing. Then we implemented the init method, which is a constructor for the class. Right, it had just a few lines of code. The first thing it did was just called deserialize and passed it all the parameters that init was getting, and then get back whatever the state that deserialize returned, which is the initial state, that was captured in this state variable. So after this step, we had two different variables tracking two different things. There is an init state variable that is storing the initial state of the player. So if we ever want to reset the game, we will just change the state to the initial state. And this state variable over here, this is the current state. So as the game progresses, this state is going to change. Then we initialized a done flag, which just signals whether the game is in progress or it has ended. The game ends when either you collide with one of the defenders or you reach the goal post. And then we created a list of actions, which is just four different strings. We are calling them north, east, west, and south, just for the sake of clarity. Could have called them anything else. Could also have used integers, but this is more readable. Right. Uh, then we called this function set rewards, which was already defined for us, and we passed it a dictionary. And this is essentially setting the rules of the game. So what how the score will change for every type of move. Then we implemented a small method called reset. The idea is, again, whenever you want to restart the game, you would call reset. Reset doesn't really do a lot. The only thing it does is override the current state with the initial state, which will bring the ball back to the top left corner, and then it clears the done flag, just in case we had finished the game previously. So if the done flag was true, it will clear it, and that's all it does. And it also returns the current state, which is bound to be the initial state, because right here we are setting it to the initial state. uh, then we implemented this helper method, which the idea was that, because the whole game is how the game works is you move from one state to another state. So this method basically found what that other state would be. So given any state and an action, which could be either north, east, west, or south, this method will give you what the next state would be. And if you look at how we are dealing with it, there is you know this dictionary that maps different types, different strings representing different actions to the change in row and column. So if you look at north, it says that the row should change by -1 because you'll go up, and the column will remain unchanged, right? And then we use this dictionary to compute our new row and new column variables. And then there is a little bit of additional code over here, because there are states. For example, the initial state, right? So if you try to go north from there, that is, in the language of football, scoring an outside, because you're trying to take the ball outside. For our game, we don't really let that happen. uh, what happens is the state remains unchanged. So that means if you try to go north, you will still remain in the same cell, top left. And that is what we are doing here, right? So if the next state is invalid because it is outside the bound of the fields, then the next state, we just return the current state. But if the next state is valid, if the new row and column are within the bounds of the field, then we just convert them back to a single integer representing the state, and we return that. This is all this method does, right? Then there was another helper method which computed the reward for any transition, right? So it will take a state, it will take a next state. It doesn't require the action, so it will just compute what the reward should be. There are again four cases corresponding to four different types of moves, so whether it's an outside or goal or opponent. And it doesn't really do a lot. It just looks up the dictionary, the rewards dictionary that we have set, and it returns the relevant reward, right? So if the next state and the state happen to be same, which mean that it was an outside, because that is the logic that we implemented here. So we just return the reward corresponding to outside. um, if it is a goal, then of course corresponding to the goal, and so on. Then there's a little helper function that was already there, which just checks if this is one of the terminal states, which means that it's either a goal state or opponent state, uh, right? And then sort of this API, which we are going to use a lot, which is the step API, which lets you play the game, or you can say simulate the game, right? And the step API basically uses other functions, other methods within the class to execute one step, one moment of the player at a time, right? The first thing it does is, so step will obviously take an action, because action is something that is decided from the outside. It could be an algorithm, it could be us playing the game. So it takes an action, it feeds that action. Of course, the state is being monitored internally. So it takes that action, and it feeds that action to this method, right? And it passes it the current state and the action that it received. And obviously it will get a next state from this method. So that is step one. Then that next state is fed to this get reward for transition method, which computes the reward for us. And then we basically check if the resulting state, the next state over here, If that happens to be a terminal state, if that is so, we set done to true, and then it just updates the state because we just took one step. So now we have moved from current state to next state. So the current state is overwritten by next state, and the done flag is overwritten with the current value of the done flag, which could be true or false depending on whether or not the new state is a terminal one. And then it returns you the next state, the reward, and the done flag. And then one of the steps that we had to figure out or complete was, just copy paste the render method. Now I just I would like everyone to read through this method whenever you are going through the class, the code of the class again. It's good to have an understanding. This is not part of the core logic, but it's still pretty prints your board. So do read through the code and see how this is working. Right. At this point, is there any confusion? Anything that anyone doesn't understand? And if you missed Monday's session, then the recording is on Slack. Please go through it and take the starter code for Monday's class. Again, the link is in Slack, and try to attempt it on your own. So once you write the code, you would have a good understanding, and all of this is going to make sense. Okay. So please stop me and let me know if you don't understand anything in terms of the logic. And of course, when you implement it yourself, then you will have a very solid understanding of why we are doing things this way. But right now, I want everyone to execute this cell and just make sure there are no errors. Cool. All right. Then the next step is just a little bit of testing to make sure our new class definition is working. So we'll create a variable out of the foosball class, and we only call the render method, which will show us the state of the field, right? This is what we expected the beginning state to be. The ball is over here. Everything is else is of course fixed, so it should look like this, right? Okay. After this, there is a step which basically where you are playing the game, right? So there is a while loop that basically takes keeps accepting actions from you, and those actions could be either north, east, west, or south if you want to make a movement. It could be R if you want to reset the game, or it could be X if you want to exit the game. So let's try to run this cell, and when you run it, you will see that it will just this progress icon will just keep running because it's waiting for your input over here. So you'll see a box below the cell where you can enter a command. So right now, the first thing you usually want to do is just reset the game. So I'll enter R, and I resetted the game. There's nothing new, but now suppose I want to move the ball right. So I will say east, and so when I say east, it tells me three things. If you look at what those three things are, these are your new state, next state, which is one because we are now in this state. This is the reward because our reward structure was such that whenever we made a valid move, there was a reward of -1. So that is the reward. And then the done flag is false because the game is still going on, right? Uh, Now I can try going south, and please follow along and let me know if there are any issues, if you're not able to understand anything. But what essentially we are trying to do is just see if it is working properly or not. So when I press south, if you look at the state, the new state is now 5, which makes sense because we were in state 1 and then we went south, so we ended up here in state 5 because states are numbered starting at 0. So this is state number 5. And again, the reward was -1 because this is just a standard move where you're moving to an empty location or an unmarked location, right? And done is still false. Is still false. Again, I tried going east, that brings me here. This is state 6, and I can keep doing this. uh, I will try to collide with this defender over here, so I'll try to do east again. And yep, you see there's a collision, and the new state is 7. The reward is -5, which corresponds to the reward that we set for a collision. And now the done flag is true, right? uh, Now let me try to do something in this state. Let's say we want to go so, right? And you see sort of a message over here which says you cannot call a step in a terminal state, and then there is some guidance on how to deal with it. But this is something that I have added, and I just wanted to show you why this is so. So let's go back to the class definition and look at this method, get next state on action. So one thing we already captured here was illegal moves, where you were trying to go to an invalid state, right? For example, trying to score an outside. That was already captured. But then there was a question of what to do if you are already in a terminal state and you are asking it to go to a next state by feeding it an action, right? And that does not really make sense logically, because the game is sort of over, you can't play it anymore. So I added an assert statement over here, and a similar assert statement in the get reward transition, so which basically catches any actions that you are trying to carry out in a terminal state. And this will just help us, because when we are trying to learn the game, if ever we inadvertently try to take an action, we'll get to know, because this assertion will be
If we
triggered
hit
and the
an
game is
opponent, it is a game over state. Where is this logic?
uh, sorry, could you be a little louder?
Yeah, basically you're saying that as soon as we hit an opponent, we reach the terminal state. Where is this
Right.
logic?
So that logic is right here,
Please tell me.
right? You mean how we are detecting, or
Okay, I want to check his terminal state. Let us see why just because I hit one opponent, why it becomes a terminal state.
yeah? So that is something that depends on the rule of the game. For this game, we want to say
Okay.
that the game is over, which is pretty much like video games. Consider
Mhm.
it as a small video game, and if you collide with one of the defenders, then the game is over. In a more realistic scenario, perhaps you would be penalized, but the game still goes on. That is up to us. We can tweak those rules in the future, but right now the rules are such that if you collide with the defender, the game is over.
So is there a way we can in here we do the step and then we end the game because we hit an opponent. But can we do a non-destructive action like saying you just try if you're going to hit the opponent then don't do the action.
Right.
That's what we
We
want to
can
implement, right?
we can add a simulate method right here, which will just simulate, and it won't actually carry out the action.
So there's no learning here, right? Otherwise, I mean, if we want to introduce learning, then he cannot go die there, right? He has to continue. So
Uh,
yeah,
no, actually, if you do want to learn, then you have to learn these parts as well, where you are not you basically don't know how the behavior will be. You carry out an action, and then you are sort of bitten by that action. That is, if you think about playing video games or in general in life, you make mistakes and you learn from those mistakes as well.
yeah. So it's like instead of actually entering to terminal state, you give a negative, very high negative
Right.
reward or something.
So actually, there are different approaches. The one we are following is just we right now are assuming it's a video game and interacting with the video game, and that means failing also. But in other scenarios, that might not be a very good idea. So we might have an additional some sort of a model that tells us that this is an opponent, and you have to stay clear of the opponent, or you have to simulate things instead of actually carrying out those actions. So I think that is best covered when we will cover something called model based learning. So we'll talk about having some sort of a model, a memory, and some interpretation of how the game behaves. Right. So if we already know that there is, and that would also mean right now, if you look at the decision making is pretty blind because uh, the agent doesn't really know anything about the defenders out there. All it cares is about valid moves and reaching the goal state. So if you want to introduce that, then you obviously need the agent to be able to see what is around it, which means when we when we talk about states, so we need to include perhaps instead of just having the position of the ball, we need to include the what other players are present in the adjacent cells or something like that, which will mean it will be the state will be a list of things, right? So coming back, if this game is running and so I tried to make an illegal move and it was caught by the game's logic. Now I'll just exit this, but everyone should be able to run this code, and if there is any issue, let me know, because now then we are going to use the same APIs to interact with the game through our algorithm. Okay, so I'm assuming you are able to run this code. Again, let me know if there is an issue with the logic, anything you don't understand about the code or why things are implemented this way. But I want to take a few minutes and talk about some of the terminology right away. We don't want to include a lot of terminology right now, like most of the books would do, but we want the bare minimum that is necessary for whatever we are going to implement in the next step, right? So first up is the concept of a state, right? So if you remember what we did in the previous week, we were talking about planning and control problems, and then we said that we will try to model these problems in terms of this setup where there is an environment and an agent. The agent is trying to learn to plan and control. You can call that decision making or whatever, but the agent is trying to learn that inside the environment, and over time we want the agent to learn it, but in the beginning we will try different approaches which may not be exactly learning. So the first thing that we want to do is have this concept of a state, which is like a description of everything that the algorithm needs, right? In our case, if you look at which piece of information we need, we just need one bit of information, which is the position of the ball, right? Because if you know the position of the ball, the position of the goal is fixed, the position of the other players, the defenders, the opponents is fixed, and then you can just try to learn how to find a path which is a short which is one of the shortest paths to the goal, and you want to avoid any sort of collision with the other players, right? So the only piece of information that we want to track is the position of the player, and that is what the state is in our case. But like we were just discussing, if you want to make the player smarter, if you want to if you want it to mimic human AI, then you want that algorithm to be able to sense its environment, and that would mean including more bits of information. For example, we can include what the position of the different players over the entire field, or we can just include whether or not players are present in the four adjacent cells, corresponding to the current player of the position. So that will depend how much information you include. That depends on how complex your algorithm is, how sophisticated you want to build your algorithm, and it will also depend on how much information you can sense. But that information is basically called the state of the environment, and that could be information about the environment, or it's not strictly the environment, but it could also be information about the agent, because the agent is sort of, or part of the agent is at least included in the environment. So in this case, if you think about how you will solve this problem, you need to know the position of the player itself, which is your agent. So uh, so uh, based on that, the state is just a number which is just telling you where the ball is, right? uh, Now this is, I think, something which is going to become more complex over time. Right now we have just one integer, we are directly telling it where the ball is. In a more realistic scenario, you just want to be able to look at a screen capture perhaps. So you're looking at a game which is just, a screen grab which is just made up of pixels, and then you want to be able to interpret what different pixels, how they are logically grouped together, what objects they represent, which objects are opponents, which object are the goalposts, and things like that. That is something very complex to do right now, but that is the eventual goal. So in the following course, for example, we will learn how to deal with pixel data. Right now, we are trying to keep the state very simple, very minimalistic. So it's just a single integer, right? Um, Yep. So we basically went over this. In our case, the state is just a number which will be between 0 and 19 because there are 20 possible states. Uh, then there's the concept of actions. That is how you interact with the environment. There are just 4 actions in our case, which are north, east, west, and south. And the whole setup is that using these actions, an algorithm will control the agent, and the agent, it will make the agent interact with the environment, and every interaction with the environment will result in the environment changing its state, right? So the agent is sort of sending an action to the environment, and the environment sends back a new state and some reward associated with that transition from the old state to the new state. This is the setup that we think will help us solve learn to solve planning and control problems, right? What is the reward? Actually, it is some sort of a signal that the environment provides you. Now, reward could be, in this case, we just get a number from the environment and we just use it as it is. We consider it as the reward. But in a more realistic scenario, the environment will give you some signals, maybe a bunch of signals, and then you are free to combine them into a single number that we will call a reward. But it's sort of up to us to combine those numbers. For example, if you're trying to move a robot, robotic arm perhaps, then you try to move it to some desired position, and then you sort of sense where the robot is, right? And when you're sensing that, then you will get a bunch of angles or coordinates, and then it's up to us to define a number uh, that represents the reward, right? So we need to combine those numbers into a single number. This is important because we want to build up we want to accumulate these rewards over time. So we want it to be a single number, the reward to be a single number. One thing that we don't want to go too much into depth right now is that in reinforcement learning, typically the reward is sparse, right? So when we are playing this game, the way we have set the rules is that at every step you are getting some reward, which could be -1, -5, 0, or +5, whatever. But generally, this is not the case. If you are trying to train a car to loop around a track, then you can try coming up with rewards for every step. But generally, uh, the situation will be something like where you get a reward if you are able to do a track, you are able to do a lap across the track, then you get some sort of positive reward. If you collide, if you go off track at some point, then you get some sort of a negative reward. So in a more realistic scenario, the reward will often be zero. So because we don't have any better mechanism to come up with a better reward, we will just leave it to zero unless something exceptionally good or bad happens, and in that case there will be a large positive or negative penalty or reward. And I'll show you in a bit what I mean by that. But we have to bear this in mind that the reward is generally going to be sparse, so don't expect a reward every time step. Okay. We already have seen this, the reward structure we have right now. So I'm going to jump into this piece of code, which is our step one that we have to implement. And the idea is that now we have the entire class ready, right? We have this step API with which we can interact with the environment. So you reset the environment and then you call step repeatedly until you reach uh, one of the terminal states. And we can sense that we are in terminal state by, the using the done flag that is returned by the step method every time you call it. So what I have over here are four different paths, which is the sequence of actions that we want to carry out. And what we want to do is implement a function called get return. And this sort of does a very simple thing. It just traverses each of the paths. So it will, for example, for this path, it will reset the game, and then it will take action E, then action south, then east, south, south, southeast, and wherever it terminates, it will keep, adding or accumulating the return. So at every step, it will add the return to an accumulator, and it will just print that return in there. This is what we need to do, and there is some additional code following this where we need to understand other related concept. But let's take a few minutes and try to implement this function. Let's see if we can implement this, if we have a good understanding of how to interact with the environment, right? So it will take a path. We will feed it one of these paths one by one, but it will take one path at a time, and then you basically have to traverse that path. Okay, so please try to write this code. I will show the solution in a few minutes, but try to attempt it on your own. And this is basically our accumulator function, and this is a for loop because you need to loop through the entire path, all the actions in the path. Okay, perhaps 2 to 3 minutes. You can look back at the method, at the function that we were just using to play the game manually, but make sure you understand it and use the same APIs to compute the returns.
Yeah, so basically we have to step and then get what is the reward in return.
Correct. Correct.
Yeah, right. And yeah,
Okay, this should be straightforward. I'm going to show the solution step by step. So the first thing we need to do is, of course, call the step function, right? Because we already reset the environment. We're sure that the game, we have reset it and it's in the beginning state. And then there's a call to render, which is optional. But if you want to just eyeball what is happening, then we have included render. But then within the loop, we call the step function, and we get the action from the path itself. The step function gives us the next state, the reward, and done. And of course, if uh, the other thing that we want to do is accumulate the reward. That was the whole purpose. So something like this, right? And we're calling this variable return, which is sort of the standard terminology. But yeah, this is the basic. If you want to optionally also see what is happening, you can include a call to the render function. And then most importantly, if we have to check if this step resulted in the game being terminated, that is so, we need to break out, right? So this is just 3 or 4 lines of code that lets you execute or simulate any of these 4 given paths, right? So let's run this, and then we are going to compute the return for each of the paths. You can see how the ball is moving, and right, so you can see sort of the entire simulation. If you included calls to render, you can see the ball was here. Then if you look at the path, it says east, so we did go east. Then if you look at it, it says south, east, south, so we went from here, we went down south, and then east, and then south again, and so on. If you look at the whole path, then it basically takes you to the goal state, right? What is the accumulated reward? Right, what should be the reward for this path? Like if you manually manually compute the reward, what should the reward be? Because corresponding to every step there's a reward of -1. And right,
Yeah,
that
minus
is
one. Yeah.
right, because we already sort of see the result, but just make sure that you understand the logic. Because there are, so you're taking 1 2 3 4 5 6 7, right? These are 7 steps, 6 steps, right? 1 2 3 4 5 6. So for each of the step you get a reward, you get penalized by -1. And then for the last step you get a reward of +5, so the sum should be -1, right? And then you can do the same for part 2 and part 3, and just look at the paths and visualize them, and you can see what is going on over here. But all these paths, they lead you to the goal state, and they all give you reward of -1. But let's like scroll back a little bit and look at what the difference was. So path 1, 2, and 3, they happen to like take slightly different approaches, but they are sort of one of the shortest paths to the goal state. But path 4 has been deliberately made a little longer, so there's a little bit of a loop somewhere or a detour somewhere. But let's see if that also reflects in the return that we get, right? So if you run path 4, then the return is -3. And this sort of takes us back to what the discussion we were having earlier about why there is a penalty of -1 even if you are making a valid move. And this was the whole idea, that if you are taking an unnecessarily longer path, then there should be some sort of a penalty, and that is the penalty that we are seeing here. So because we took two additional steps which were unnecessary, we could have taken a shorter route. So your return is -3, right? So in terms of terminology, reward is what the signal you get at each time step, and return is the accumulated reward over all time steps, right? Okay. uh, let's move to step 2 and change the reward structure, right? And we were just talking about the rewards being sparse in most of the realistic scenarios, so you don't get any reward at all for each step. If you look at the reward structure that we want to set now, so whenever you are making a valid move, there is no reward at all, it's a reward of 0. But whenever you sort of make a mistake, if you run into an opponent or perform an outside, you get a reward of -1. And whenever we hit the goal state, of course the reward is +5. So the only thing that has basically changed is this reward has been made 0, which means that in a lot of cases you won't get any reward, and we still have to learn to make those decisions, right? So what we want to do here is just override the reward structure with the reward structure that you see here, and there is already an API. So just take a minute and implement this step, and then we will see how the returns vary. Okay, I won't take too long here. It should be straightforward again. And I'm just copy pasting from my solution, but this is just 2 lines. So we already had this API set rewards. We are just passing this updated dictionary to this API. But before you do that, make sure you have called the reset function, which is there to ensure that you don't change the reward in the middle of a game. So it's just a safety net. And I do this, and then we again call the same get return path, get return function, just comparing two different paths this time, path 1 and path 4. Path 1 was shorter, path 4 was the longer one, right? Uh, this time the reward will be different. There is no penalty at every step, so the only reward you get is at the end when you score a goal. So the reward is overall positive +5. Um, but if you look at the reward for path 4, which was the longer path, the reward is again +5, right? Uh, yes, right. So this is sort of a problem that we want to fix, because overall, in most of the cases, we want to find a shorter path, the shortest path. So we cannot, have this system alone where you just accumulate rewards. So the accumulated reward will be the same if the immediate reward is 0 most of the time. And how we deal with that is through discounts, which is a very simple idea. All we need to do is we need to take the current reward whenever you're computing a return. Take the current reward, but then when you're trying to accumulate the reward at the next step, then multiply it by a small number, a fraction, which is like zero point 0.9 or something. And this will ensure that even if suppose all the intermediate rewards are 0, right? These are all 0, and then you get some RTN at the nth step. This time number will get multiplied to a high power of gamma, which will ensure that it is the overall value is lower, because earlier when there was no discount, then there would be no gamma here, and you will just end up with RTN, right? Sorry, you will end up with RTN, which meant that we were getting the same reward every time. So this is what we have to introduce in step 3. So this we have to implement this function get discounted return, which is going to look a lot like the get return function that we implemented earlier. But now uh, this should give you the discounted return, and this is how you compute the discounted return. So again, let's take some time, a few minutes, and try to implement this. Let's try to implement it and then run the next 3 cells, and then we should get a more sensible return. So path 4 should have a lower return than path 1. Yeah, from now on we are using the updated reward, and it is the updated reward that is causing problems to us, because with the updated reward being 0 for valid moves, you get the same return for a short path versus a longer path, and that is what we want to fix with discounts.
Do you want the geometric series? Okay.
Yeah, basically this exact formula, it's the
Okay.
product
Correct.
of a geometric series with the rewards.
Okay. Yeah.
Right, so I think 2.65 is what you should get. Yeah, around about 2.65 for path 1, and part 2 would be around 2.15. Correct. And most of the logic is just going to come from the get returns function. The only thing is you now need to multiply by this factor before you accumulate. Right, so I'm going to write or sort of copy paste my implementation. So I created this variable up front, which will be the coefficient. Initially this is set to 1 because gamma is 1 for the first step, and then sort of the rest of the code is just going to come from the implementation that we did earlier. Right. Yep. So this for loop still remains the same. This first step is still the same. The only thing that changes is that now I multiply the reward at that time step by the discount coefficient, and then I also update the discount coefficient by multiplying it with gamma. So every time it gets multiplied by gamma, which means it becomes higher power of gamma. Uh, we can quickly run it, and so in this step we are creating uh, a list, actually a dictionary, which will just keep track of all the hyperparameters, right? And gamma is one of those hyperparameters. This is not something that we are going to be able to learn from interaction. This is something that we have to set based on trial and error or experience or some other methodology, but we are not going to learn it. And then if you run this method for the first path, get 2.657. For the second path, it's around 2.15, which is sensible now because the second path was slightly longer, so the reward is slightly lower. The return, sorry, is slightly lower. Right. Okay, so now that we understand this concept, we will try to use the concept of return to formulate our problem, which is finding the shortest path and scoring a goal. Right. And what we essentially want is described over here is that we want to reach the goal post and we want to attain the highest discounted return. So we just introduced the concept of discount, so we want the discounted return to be high. We want to find the path which corresponds to the highest discounted return. Right. What does it actually mean? In practice, it means that you don't run into opponents because obviously you don't want to pick up penalties. You don't want to be stuck taking actions which just waste your time, like creating outside, performing outsides, or taking any a longer path. So you want to be efficient about all these things, right? Now, here is sort of the problem that we will be solving for the rest of the course, which is how do you do that, right? We know that if we know the path with the highest discounted return, that gives us the solution. We will just simulate that path, and we can reach the goal state. uh, the simplest way would be to just generate all the paths, start from the beginning and try different actions, enumerate all the different paths, and of course for every path we can pass it through this function, right? Get discounted return, it can give us the discounted return for every path. So just compute the return for every path and then rank them, and whatever path is at the top, that is the one with the highest return. You need that path. um, but if you look at it, that is not really possible even in a very small tiny game world like this. The number of possible paths is really huge because because if you think about how those paths are created, you need to make a decision at every state or in every cell as to whether you want to go north, south, east, or west. So there are essentially four possibilities in every state, and then if there are 20 states, so you can imagine that there are roughly 4 to the power uh, 20, right, possibilities, because in the first state there are four possible moves, and then you pick one of them. In the next state again there are four possibilities moves, so it is the number of possibilities is a product of the individual possibilities, and which is like 4 to power 20. And even if you include some of the invalid moves, even then that number is going to be big enough, right? So the brute force method, we don't want to use it, even though it might be sort of feasible for a small game like this one. We don't want to use that, which means we cannot enumerate paths and we cannot rank them, right? Then the sort of trick that we use is that we realize that okay, we cannot compute the discounted return for every path, but we can still do that for every position on the game or every cell on the game, right? And because all the paths are made up of essentially these 80 different possibilities, right? 80 state action pairs, right? So if you think of any of the paths, right, let's any of the paths that we define, so it is just a sequence of states and actions. The state is implicit here. We are not doing that. We are not including that here. But the state is being maintained internally by the game. So initially the state is 0, and then the action is east, which is like the first thing in our path, and then the east action will take us in state 1, and then the new action is state south, action south, that takes us into state 5. But so essentially every path is just made up of these pairs of state and action. That is what we are trying to use over here, right? So yep. So any path that it is going to be made up of these 20 different state and 4 different actions, so 80 possibilities. So the idea is, what if we can find the discounted return, the highest discounted return that you can get for state and actions, and then let us see if we can use that information to find the best path without actually having to enumerate the paths, right? And just want to doubly emphasize that we want to find the return for every state and action. We're not interested in the reward, because the reward you can just look up the uh, API and you can compute the reward. We want the return. But the return basically depends on all the state and an action that follows any state and action. So for example, if I talk about what will be the return for state 1 and action south, I cannot answer that unless I'm told what are the following states and actions. So I need to know the entire path. So the problem really is how do we circumvent this thing, right? Because return computing returns requires an entire path to a terminal state, but we are saying we don't want to use the concept of path. We just want to find the return for a state and action pair. Is this making sense? Okay. uh, right. So and this will make more sense once we start writing the code. Yeah, we yeah. So the trick part is that, okay, we cannot enumerate the paths, we cannot find the return for every path. So let us try to solve sort of a simpler try to solve a simpler problem, which is finding the return for every state and action pair. So instead of worrying about the entire path, let us just find the return for every state and action pair. And the idea is that if you are able to do that, then perhaps we can piece together that information, and we can tell which path is the best without actually enumerating the path, without actually simulating the path, because that is the hard path. You cannot simulate all 4 to the power 20 paths realistically. So uh, we are going to attempt to solve a slightly different problem, right? And that problem is finding the return for every state and action pair. And as I mentioned, we still don't know how to do that, because finding the return basically requires you to follow a path. You follow a path, then the path ends somewhere, and then you start from that state and you look at all the rewards that you got along the way until the path terminated, and you sum them up. After discounting, that gives you the return. So the question is, how are we going to find the returns if we don't want to simulate the paths? And we are going to look at that. But let us first start with, by building a data structure that is going to store that information, right? So if you look at my screen in step 4, I'm going to implement something called a rewards table, right? And the idea is very simple. It will have a row for every state. It will have a column for every action. There are 20 states, right? And there are 4 different actions. It is going to be a table of some sort with 80 columns, right? And I'm going to use a pandas data frame. Uh, it's okay if you have never used pandas earlier. It is really simple. I'll explain how this is working. But I'm creating a variable over here, a data frame, and I'm doing so using dictionaries. So uh, let me first run the code and show you the output. So this is what I wanted to construct. There are 20 rows 0 through 19. There are 4 columns. They are labeled with the actions, which looks pretty: north, east, west, and south. And all the entries are none for the time being. So there is no valid value over here right now. If you look at the code, it is right over here. So this constructs a dictionary, right? This is a for loop, right? So if you look at this is for a in foosball.actions, which will just, you know, so a will assume the value north, east, west, and south one by one, and then it is mapping all the actions to none. So it creates a small dictionary. If you just want to look at it in isolation, then right, if you just look at this part of the code, this is what it does. It creates a dictionary, and that dictionary has all the actions, and those actions are mapped to values which are all none. And then if you look at the larger thing, so this is again a dictionary, but now the for loop is over the states, right? So now the for loop is the s is going over the number of states, right? And what this is doing is it's creating a dictionary of dictionaries. So it is basically creating a dictionary for first row, then for the second row, for the third row. For the first row, the state is going to be 0, uh, and the value is going to be this dictionary over here. For the second row, it's 1, and the value is again this dictionary. And it is on nuns right now because uh, we are creating an empty table. So this is just a shorthand. You can do it in different ways. You can perhaps create a NumPy array and then create a pandas data frame out of it. As you can see, I'm calling from dictionary. So it's taking a dictionary and trying to create a data frame, which is like this table. And this orientation thing basically tells you how this table will be oriented. So whether you have north, east, west, south as rows, or whether they will be columns. And so just make sure you're able to run and understand this code. But this is creating an empty table. We are calling it the rewards table. And then there is a little bit of code over here. So this code goes over. I'll try to show you what is right. So because this is a pandas data frame, we have access to a few variables. Like if you call rewards table.index, it gives you the indices, which are basically the states for our game. Likewise, if you call columns, then you get the header, the column headers, which are north, east, west, and south. So they get printed. So we're using that. So there's a top for loop which goes over all the states, and then we just test if the state is terminal or not, right? And if the state is not terminal, right? If there's a not upfront here, so if the state is not terminal, then we loop over all the actions. What we are essentially trying to do is fill up this table. It's an empty table filled with nulls. We want to fill it up with the different. So for example, state 3, and let's say action west. So what is the reward value for this combination? We want to fill up the table with that value, right? So this other for loop is going along the actions, and then all we need to do is call this API, because we have a state over here, and we also have an action over here. We can pass them to this API, and it directly gives us the reward that is expected from this state if you perform this action. And then that basically gives you the next state, not the reward. That gives you the next state. Then we feed the next state to this other API that gives us the reward, right? This is how you would fill up the table. You have two different APIs. You have a state action. You use the state and action to get the next state. Then you feed the next state to the other API, and you get a return. And if I run this cell, and if I remove these two lines for the time being, if I just right, so this is your rewards table. This is nothing new. We already knew this information, but we had to call this function every time. We had to call this couple of functions, but now we have the same information as a table, right? So if we for example, we know that if we are in state 0 and if we want to go north, then we will get a return of -1 because it is an invalid move. If we want to go east, we will get a return of 0 because it's a valid move to a blank state, and according to the new rules that gives you a 0. If you want to go west, again you are blocked, you are trying to score an outside, you get a -1. If you go south, it's a return of, it's a reward of 0 again, right? This should make sense to everyone. Just copying the other two state, right? The other two lines, and I just created a variable over here which gives me all the terminal states. So which is 2, 7, 9, 15, 17, 19. I did so to verify that only the rows corresponding to the terminal state are blank. You can see 2, 7, 9, and then 15 and 17 and 19 are the blank rows. The rest of the rows have been filled with the right reward value. Okay, but this isn't really what we are interested in. I did this just as a demo, just to show you how the table should look like and how it should be filled. But we want to construct another table because remember we are after returns. We are not interested in rewards, right? So what I want next everyone to do is create a similar table. Let's call it the return table, right? And what we have to do is we have to basically complete this method, this function over here, make returns table. The logic is going to be exactly what we saw here. For the time being, we are again constructing an empty returns table, but the instructions are over here. So now we want to fill everything with zeros, and I'll come back to that in a little bit.
One second.
Why?
How did you
Yeah.
introduce a new cell just
uh,
above? Yeah, this 26.
this one, right? So there are two ways. One is like when I'm hovering over a cell, right? So right. So normally when you when you hover over a cell, you see this code and text option. So if
Oh,
you can click on code, and that adds a code cell. If you want to add text, go for text. There is
yeah.
also a keyboard shortcut. So if you press Control plus M, which sort of activates the key binding. So press Control plus M, and then if you press B, it will add a cell below. If you press A, it will add a cell above the current cell. Okay, discount returns.
And what does that plus text mean? Oh, text
Uh,
cell or code cell? Okay, I got it.
yeah, text is markdown and code is code. Okay, so let's try to write this piece of code which constructs a table again. The logic is going to be exactly the same as earlier. The only difference is the initialization, and the description is here, but basically we want to initialize everything with zeros. Yep. Please read these instructions carefully and then implement your code. You can copy paste from the previous implementation where we created a similar table, but there are small changes. Okay, so like I said, the most of the code is going to be same, and it was practically a single line of code. So we have this function that takes a list of state, a list of actions, and a list of terminal states, right? And we are trying to create a table. We use the exact same code. So right, only the only things that have changed is that now we have an action list. So A is looping over action list, S is looping over a state list over here. So this creates a table, and if you look at it, everything is filled with none right now. But if you look at the instruction, it says that the return for all actions in every terminal state. So basically, every row corresponding to a terminal state that should be filled with zeros, and that is the only change. And there is an easy way to do that when you're using a pandas data frame, right? So right, the table is a pandas data frame. To table dot location can be used to find, you just extract a subset of the table. In this case, we know a specific row, so we specify uh, not a specific row, a bunch of rows. So this terminal state is a list, right? And it's in pandas it's possible to uh, index into a specific rows using this syntax. So if you pass it a list of things, and you can actually test this code outside the cell as well. But in just one line of code, we are able to set all the terminal states, all the actions corresponding to them to zero. And if you run this, so you should get something like this. And again, printing terminal states, so they're visible. So all the terminal states, they are filled with zeros. For example, 2 and then 7 and then 9, these are terminal states, they are filled with zeros. Everything else is still filled with nulls, right? And this is pretty much like what we did earlier, but only a little bit of difference. But now this is the returns table, and the focus really is going to be on how to fill up this table, right? So for example, I want to know what is the return that I can get for state 0 and action north, right? But I cannot answer that question right now, because all I know is that, okay, I want to take action north in step 0, but then I don't know what actions I want to take after that, right? There are a huge number of actions that are possible, and that will take you through different paths, and that will terminate differently. How can I know the discounted return for 0 and not, without actually simulating those all of those paths? And that is the focus of the rest of the notebook, right? So one thing I want everyone to look at is, let's go back to the definition of discounted returns. And there is a pattern that I want everyone to understand and appreciate, right? Look at this discounted return, and I will take a second. Right, so I'll go down and paste this, only the formula.
Around, can you show me 29, 20,
uh,
28?
28, cell number 28.
I'm getting an error when I run this 27, line number 27.
What does the error say?
Um, trace back. Table is not, oh, okay. Okay, I got it. Right.
Sure. Right. So I pasted this formula again. Yep. So I wanted to paste this formula again because I wanted to make it a little clearer. So when we are saying discounted return, then right. So let's call it dr, just to abbreviate. So we're talking about the discounted return in, I'll change things a little bit, but yep. Uh, Yep. Just change formula a little bit. So the notation is consistent. So instead of using t, we are saying that this is the reward that you get in state zero, and then this is the reward that you get in state one, and so on. This is the reward that you get in the terminal state. Uh, and to be more specific, this is the discounted return corresponding to state S0 and action, some action A0. Right. That is not visible over here, but this because we were simulating an entire episode. So obviously in S0 we took some action that took us to state one and so on. So when we are talking about returns, this is the return for state S0 and action A0. Right. Now let us also look at what the return looks for starting at the next state. So if we were to start here in S1, if we forget about S0, if you start here, then obviously, right, so if we talk about S1 and A1, whatever A1 is, so we can forget about the return, the reward from S0, and we need to remove this gamma because this is the first return, right? This is what the sorry. So let's look at the formula. So this is the discounted return for state S0 and A0, and this is the discounted return starting at S1 and A1, right? So there will be the immediate reward. I'm sorry, this has to change a little bit. This will be gamma, this will be, right? This should be the formula. If is this like, are you able to connect the dots, or are you able to understand why this should be so? If we were to start in S1, then this should be the reward, this should be the return, the discounted return, because you have the immediate reward, then you have the discounted return for S2 and so on.
Gamma to
uh,
the power n minus 2 should be, right? Because you have one less
right,
step.
this should be in -2, this should be in -2, and this should be in -1. Right, thanks for the correction. So the terminal state is still the same, but now we are starting one step ahead. So of course the power of gamma has changed accordingly, and you only reach up to gamma power n -2. uh, and there is a relationship between these two equations. There's a beautiful recursive relationship between this equation and this equation, and that is sort of the backbone of the rest of the work that we want to do. Right. So can we attempt to write as marked down? Just add another line. Can we attempt to write dr of s0 a0 in terms of dr of s1 and a1 and whatever additional terms are needed. Let's say something like this. So what we want to do is dr of s0 a0 is equal to something this sort. I'm not writing the exact formula, but this is the idea. Can we write dr of s0 a0 in terms of dr of s1 a1? Give it a try. This is really important. It's crucial to, because then we are just going to translate this into code.
It's R of S0 plus gamma star dr of S1A1, right?
Correct. So just looking at the equation, and if you think intuitively, that is also clear that the difference will be that now you will get an additional reward, right? And then if you look at how gamma is being multiplied, you need an additional multiplication over here, right? Is this evident to everyone how this relationship holds? Just look at the returns, that the rewards that you're adding up here. So here we are starting at r1, but for s0 a0 we had r1 multiplied by gamma. Here we have gamma into rs2, but here we had gamma square into rs2, which made sense because we had started one step earlier, so the powers of gamma were higher by one notch. And if you can see, this dr 0 is essentially the immediate reward. This is the reward that you get when you take when you take a state s0 and take action a0, and that leads you to state s1. So this is the immediate reward, and then the rest of the thing is this whole term over here, right, which is the discounted return for the next state. This should be clear to everyone. If there is any confusion, let me know. But if this is clear, then we can talk about what we are going to do in step 6, right? So we did this by following an entire episode, right? That is how we got all these rewards, right? And that is how we got this equation, right? But what if we want to do something similar but without having to follow an entire episode? What if we just want to look at one step of that episode, which is the transition from state 0 to state 1? Can we still apply this sort of a recursive relationship?
So
And that is what,
I have one question. I'm a little
yeah.
confused here. So when we are in, so basically I'm confused about this action pair that is being added. So say we are in state 0, right? And we have taken the action 0. That is what led us to state 1, and
Right,
hence we are taking the reward for state 1, right? That
right.
is what. So then when we are doing this recursive relationship, where are we? So when we are doing this R of S2, where are we capturing what action we took that led us to R of S3?
Yeah,
As in
right. So,
this.
yeah, so the actions are obviously not visible here. I mean, we can add actions that will make more sense. We can add, sorry, we can put action over here, something like
Okay.
a1, right? And that completes the notation. But the thing is that if you think about how we were using it, the actions were coming from outside. We were feeding the actions, and the state transition was sort of happening inside. So actions are implicit, but like actions are known. We should understand that there is an action accompanying every state, and that is how we are able to figure out, because these are all variables s1 s2. So S1 doesn't really mean the first state. S1 could be anything, and S0 could be anything. So what, depending on the actions, they will assume exact values.
So in this formulation, each state is also associated with an action. When we
Right.
are saying,
Right, right. So, for example, let's say state S0 is, let's say actually state 5, right? And action is west. So that is your first pair. Now I'll look at, okay, what will happen if I were to take action west in state 5, and probably it says that I have to go to state 4. So S1 over here then will be state 4, and then again in state 4 I have to look at what action I took according to the episode, and simulate that.
okay, thanks.
Sure. And just uh, perhaps trying to run the code a few times. So perhaps writing it down with pen and paper. Start with some other state. Don't start in a state S0. Start somewhere else, and then see how this equation looks like. But if this recursive relationship holds, then we can write a similar recursive relationship when you don't have the entire episode, right? And the idea is that we are interested in the highest discounted return, because there can be many discounted returns for the same state and action, right? Because the return basically depends on the rest of the chain of events until you terminate. So we are only interested in the highest return that we can get, and we can write a recursive relationship which is exactly this relationship sort of, but with a little bit of change. So over here we have the return for state T and action T, and on the right hand side we have the immediate reward, which is a function of the current state. Sorry, which is a function of the current state and the next state, right? Which was this thing RS0. Right? Now there's a difference of notation. This is the reward is basically, it depends on S0 and S1 both. So it's actually a function of state T and state T plus 1. But this is the reward part. Then you have the gamma, which is the discount factor. But now instead of selecting an action, because we don't know which action will be followed, there are all the possibilities are open. So in from state 1 we want to find the return for this specific state and action, so this action is fixed. But over here we don't know which action we want to follow, so we should be open to following all the four different actions, which is north, east, west, and south. And what this equation does is it takes a maximum over all the four returns that you can possibly get, right? So the only difference between this and this is the introduction of this max, and then there are these four different values to pick from instead of a single value. Because now, earlier we were following an episode, so we knew exactly which action we would take in state one. We had taken in state one and state two and so on. Right now we don't have that, so we will just see what is the maximum we can get from all the four actions combined. Does this make sense? This conversion?
Is this not like Digextra?
Yeah, it will look like a lot of algorithms depending on which domain we talk about. This can look like Dijkstra's, this can look like dynamic programming, for example the YWB algorithms, or anywhere where you, because all of the dynamic programming uh, you know equations are going to look like that. But essentially this is nothing but one step of a recursive relationship. And what I want everyone to understand is why we need this max and these four different terms over here. Because on the left we are interested in finding the maximum return, and the reward part is fixed because the state and action, we have decided which state, which action we want to find the return for, so that is fixed. So the reward gets fixed. But now and that also fixes the next state, so the next state is also fixed, but the action in the next state is not fixed. So we must find the maximum return corresponding to all four actions, and we should use that maximum return to update the return for state T and action T. Cool. Okay, and you might have to like ponder a little bit more over this equation. If there is any confusion, let me know in Slack. I'll try to explain. The idea is really simple. Just take one step, you will get a reward, and then see which next state you have ended in, and see what is the best return that you can get. I want to emphasize that over here it's return again. So what is the best return, right? And this is just a recursive formulation that we can just try to solve recursively. Like if you want to uh, can we solve with one dimensional array? In what sense? You're saying the table should be one dimensional? Yeah. So the thing that we are interested in is state action pairs. We can do that. We can only have states, and we can formulate this similar equation for states as well. But because we are interested in decision making, we want to store the information for every state and action pair, because then we'll be able to tell which action corresponds to the highest return, and that is the action that we would like to take in any particular state. Cool. So look at this closely. But what we essentially need to do in step 6 is we want to implement this as it is. It's pretty much like a recursive equation for simple things like Fibonacci series or any sort of recursive equation, uh, and we sort of know that is why, if you think about why we filled these values with zeros, these terminal state is because we wanted to use to be able to use a recursive formulation like this one, and then you need some terminal point where you can just look up uh, that value and say, okay, the computation terminates here. This value is already known to us. This is the base value. So that is why these values were filled here. But now we want to use dynamic programming to fill it up. We have the equations, we have a table where we can store whenever we compute the state and action, this thing for one of the states, we just store it in the table. The next time we want to access it over here, we can just look it up. If the value is not present, then obviously we need to make a recursive call. But now I would like everyone to implement this part, which is some of the starter code is already there because we want it structured in a particular fashion. So I'll walk you through what the code says. It takes a table, which is going to be this table, and then it takes a specific state and action, right? And there's another parameter called debug, which we'll use later. But then if you look at the if condition, then it basically, yeah, if the table, if that state and action pair correspond to an empty location, then you sort of try to perform this computation, right? And if that is not the case, then there is nothing to be done. We already have the value in the table from the previous computation perhaps. So there's nothing essentially that needs to be done. So all this is doing is trying to fill up one specific location in the table, and there will be recursion, because if this is the case, right, if the current then obviously you will want to look at the next state, and because when you try to access the return for the next state, there will be recursion, and we want to use this equation to implement that recursion. So now we have around 20 minutes or so left, so I want to I want us to go to breakout rooms and give this a try. This will require a little bit of thinking, a little bit of experimentation, um, but yeah, let's try to implement this. please go to your assigned room and try to implement this. If you are able to implement it early, try to help others and discuss the solution, and then we'll come back and look at my solution. Okay, so I went and checked on a few of the breakout rooms, and there were some good conversations happening, and people were trying to help each other. I know, it's not. It will take some time if you're doing it for the first time, and I don't expect you to finish in these 10 minutes. But we sort of came back because we are, low on time, and I wanted to show you what the solution should look like. We have a couple of other steps where we will make some improvements, so there is enough to implement ahead. But if you look at this code, so there is already a little bit of hint, right? So what we are getting in terms of input is the table and the current state and the action. And if you map it to the equation, this is the current state and the current action that we are getting. But if you look at what we need on the right hand side, we need the reward, we need the next state, and we need next actions. So there's a lot of things that we need. So really the first thing we can do is just also find the reward because we already have the next state. So just pass that next state over here and find the reward. And then there was a little bit of debugging code that will just leave intact here. But what we need to do next is should be just one line of code. It will take a little bit of time to figure out, but this will just mimic the equation that we want to implement, right? So again, I copy pasted it from my solution. I just want to make sure that there is no subtle bug that I introduce. But just look at this equation that I copy pasted, and this is pretty much like this equation over here. There are a few differences. So of course we want to fill up this position on the table, right? State corresponding to state t and the current state and action. That is what you have on the left hand side. On the right hand side, you have the reward, then you have gamma, and then gamma is being multiplied, and then we are taking the maximum over the four possible next actions, and that is what you have inside the max, right? So there is action 0, action 1, action 2, and action 3, and we want to compute the maximum return for this state and this action for the new state and action action north and next state action east and so on. We still don't know if those actions are already present in the table or not. So to be on the safer side, we just call the same function, call the compute returns v0, call it again, but this time on the next state, right? So it's the next state over here, and then the first action, next state, second action, next state, third action, so on. This is the idea. This pretty much looks like the equation over here, but if we were to actually run it, if you run it, and if you go to the next cell, so
I
we
think
will remove
you
this
did not
for loop.
introduce the termination condition for the recursion, right?
Right. So right now I'm attempting to fill just state 0 and action is equal to north, right? And let's try to run this, right? And the moment you run it, you realize that there is an error. It's actually a stack overflow, right? This says maximum recursion depth exceeded, and fortunately we already have debugging logs which we added in terms of print statements, and if you look at it, it is basically printing same message over and over and over starting from the very beginning.
So we
Which
have to
says
take
trying
care.
to fill state 0 not 0, which must be getting printed from here. So the
Yeah.
state is 0, action is north, next state is 0, which makes sense because action north in
Unmarked.
state
Yeah.
take you
Unmarked state.
take you back to state 0, right? And that also sort of tells us what the underlying issue is. We passed it state 0 and action north, and now next state is again state 0. So if you look at these four different calls, one of them is again going to be state 0 and action north, this one in fact, right? And this is just going to be an endless recursion which will cause your stack to overflow, and this is a bug. We need to fix this. We know this will happen for every state which has which has one action, at least one action that brings you back to the same state. So at least all the states that are on the border of the field, they are going to have this shape. Right. That is one thing. We will fix that tomorrow. Uh, but the idea here was I had a for loop over here because I want to make sure that all my starting states are filled, right? So for state 0, I'll call it for all the actions, and then hopefully this will fill up the rest of the table as well. But in the current form, we already have an issue. This is not working even for one cell, but this is roughly the idea. Now in step 7, we are going to refine this idea. If you look at what is, it's not exactly step 7, but the second part of step 6 is where we want to cache this sort of self recursion, and then hopefully be able to fill the table, right? So this is something that I want everyone to look at and try to uh, fix. So this is going to be just look a little different from the code that we just saw, and it will have a condition which will catch cases like this. Essentially, when your state and next state are the same, then you don't really need that bit of computation, the recursive call. So catch that early. Try to implement this, otherwise we'll look at the solution tomorrow. But we'll see that even with that added guarding condition that catches self recursion, there are issues. There will be issues with mutual recursion, and we'll think about why this is happening. This does not happen in normal circumstances when you are using dynamic programming. So also think about how this is different from a standard problem where you apply dynamic programming, right? Because it seems to be something that you can solve with dynamic programming. There is recursion, there is overlap, because when you start with a state, you go through different subsequent states. When you start from some other state, again at some point you will reach the same subsequent states. There will be overlap. So it seems to share sub problems with within different problems, uh, but still we are running into infinite recursion, indefinite recursion. So think about why that is happening, and we will discuss that tomorrow, and we'll continue from there. We will take an approach where we don't have to deal with the recursion at all. That will happen in the next step. And then once we figure out how to use dynamic programming, or whatever you call this approach, which is similar to dynamic programming, uh, then we will see, once the table is filled, then we will see that there are a few other things that we need to do, because we can't get a good enough estimate in one iteration of the table. We'll talk about all that in tomorrow's session. But do give it a try. Try the second and third parts of step 6, and try to understand what is going on and how that can be fixed. Are there any questions? Okay, if there are questions, please ping me on Slack. Try to implement this. Then we'll meet again tomorrow, and then tomorrow we'll work out the first solution, working solution, that will give you the shortest path. Uh, it won't be nothing very novel because we are still not learning anything. But then once we have that figured out, then we will take the first step in the direction of actually learning how to do this instead of using a known solution, because then when we in a more dynamic situation, things are changing, then even this solution will not work. Okay, cool. Thank you so much for attending today's session. Please make sure you keep attending the sessions, tomorrow sessions, and the office hours. It is only going to get more interesting from here.
Thank you, Farhan.
Thanks. Bye bye.